is the producer.
The vertical translations of functions. So as you can see here, this is a basic layout or formula of what a function is supposed to look like. And in order for vertical translations, we look at the variable c, and for horizontal translation, we look at the variable d. So we'll be taking a look at both of those today. But first of all, I just want to direct your attention to the y equals x squared function here. As you know, this is a base graph, and that's graphed over here. This is a regular graph, and this is a function, and the way we can tell is, number one, it passes the vertical line test. So if you're to put a vertical line through any part of the graph, it shouldn't have more than 2 points intersecting it. And this is exactly what it means to be a function. There are no two of the same x values with the same y values. So essentially, no 2 points overlap. And as you can see in this part over here, the domain of the function is x can be any real number. And that's because x, this parabola is infinite, as shown by the arrows. It can keep going, which means it can go all the way infinitely throughout the x-axis. For the range, y, it's different. The reason why is because it stops over here. So the way we write that is y is equal to any real number such that y can only be greater or equal to 0. And common logic will show you that 0 is over here, and all the y values can only be greater or equal to 0, and that's why we have that. Now, back to horizontal and vertical translations, I'm just going to start by talking about vertical translation, which is shown by the variable c. Now, the one thing to remember about vertical translation is always written at the end of the function, at the very end. So, when you want to write that something is translated vertically, you use positive and negative signs. So if you want to write that something is translated up 4 units, write plus 4. If you want to write that something is translated vertically down 4 units, you write down 4, which is dictated by the negative sign. Now, in order to graph one of these, this graph over here, there are no other transformations on the function, so you just move this parabola down 4 units essentially. So from 0 to negative 4, and the rest of the graph is essentially the same as the parabola above it, just translated down 4 units. So a rough sketch of it would look like this. Now, the domain and range for this, because it's shifted down 4, the domain would still be the same. Nothing happened to affect the values on the x-axis, so the x is equal to any real number. But for the range, since before y was equal to any real number, once it's greater than or equal to 0, now since the vertex has been translated from 0 to negative 4, the domain is now y is equal to any real number such that y is greater or equal than negative 4. And that's how we draw that. Now, talking about horizontal translations. Horizontal translation is represented by the variable d in that case. And this is always in brackets. So take the x out from here, and when we're drawing it in brackets, if we want to go up to the right or to the left, it's a bit different because the signs are the opposite in horizontal translations. So if you want to go to the right or towards the positive side of the axis, you would write a negative sign. And if you want to go to the left or towards the negative side of the axis, you would write a positive sign. So, for example, if you wanted to go right 3 units, you'd write minus 3, and this would be in brackets. Now, if you wanted to go left 3 units, you'd write plus 3 in brackets. Okay, so x plus 3 squared. Oh yes, I apologize, I forgot to write the squared on the formula here. So when we're writing this function, now as we know, this is translated 3 units to the left. To graph that, essentially the same as the other translation, nothing from the function changes except for its position. So you just move it 3 units to the left. So it goes from here to, from here to over here. So now the graph looks roughly like this. It's essentially the same, just translated 3 units to the left. And that was shown by adding a positive sign inside the bracket after the x value. Now for the domain and range of this, lastly, the domain would be the one that remains the same because nothing happened to the x values. But the range, once again, remains the same as well. And the reason for this being is that even though it's been translated, even though it's been translated, the same restrictions apply to the domain and range. Now just to explain that, on the domain, the x values can still go on any part of the x-axis infinitely, but on the range, it still can only go equal to or above 0. And that's why we write it to y can equal any real number such that it's equal to or greater than 0. Thank you. Just one thing to add on about the graphs here, in terms of horizontal and vertical translations. Now the base graph, y is equal to x squared. This, in terms of mapping notation, is written as so. Now this just means the coordinates of the parabola are 0, 0, 1, 1, etc. Now when you're translating that graph, you need to adjust your terms. And the way you do that for vertical translation is you adjust the y terms. So for example, in our same parabola we have over here, where it's down 4 units, you would write -4 to each term. This way, all of your y values are being translated down 4 units, making your whole graph go down 4 units. That way, your final set of terms would look like so. And this is just to represent the terms of the new graph. So as you can see here, it starts off at 0, -4, then it moves to 1, -3, and then it goes on 2, 0, etc. So this is just to represent what the graph looks like in its terms. For the horizontal translation, instead of writing it on the y side, where the y terms are, you would move it to the x terms. So instead of, take this example, when you're moving it to the left 3, instead of it being +3, it's now -3 over here. So essentially what this does is translate the whole graph left for you. So the final graph then would look the same on the side of the y values, but would be translated on the side of the x values. Now this is just what it would look like in that sense.
We'll be talking about reflections upon the x-axis and upon the y-axis. So here I have put out the coordinates for the y equals x squared, the root x graph, and the 1/x graph. So I've drawn out each of the original graphs here and plotted the points. So to start off with the y equals x squared graph, we'll be doing a reflection upon the x-axis. And to do a reflection upon the x-axis, you must multiply all of your y values by a -1. Doing so, you essentially flip your graph upon the x-axis. So I'm going to draw that out here. Alright, so that's when you reflect upon your x-axis. And for this particular graph, when you reflect upon your y-axis, nothing really changes because you can't really switch over to the y-axis here. So now moving on to the root x graph. So as you can see here, the base graph for the root x graph goes like so, and here are the coordinates. And once again, to reflect upon your x-axis, you multiply your y values by -1. So after you do that, it'll look, so it's like just like the other one, it'll flip upon your x-axis. And draw the arrow at the end. Alright, now for this one, if you try to reflect upon your y-axis, it'll work. So you do the exact same thing. You multiply it by -1. Alright, and then once you do that, it'll look something like that. And the numbers will be down there. Okay, now for the 1/x graph. So I've done the 1/x graph here. And now to reflect it, you do the exact same thing, multiply it by -1. And I'm not going to go through it there, but I'm just going to draw it out here. So this is going to flip like so. So it'll look like that. And then this one's going to flip over there, and it'll flip like that. And here you can label, if you like, your asymptotes. These are your asymptotes. Okay.
Now we're going to be talking about section 2.5, vertical stretches and vertical compressions. Vertical stretch or compression is when you multiply the y value of a function by a certain number, and we refer to that as variable a. So if the a variable is greater than 1, then it's a vertical stretch. If the a variable is less than 1 but greater than 0, then it's a vertical compression. Moving over here to our function y equals fx, the a variable comes before the f. So let's say we were vertically stretching it by a factor of 2, that would be y equals 2fx. So in our table with the x values of 0, 1, 2, 3, and 4, y would be 0, 2, 4, 6, and 8. So drawing that over here, that would mean it would be 0, 0, 1, and 2, 2 and 4, 3 and 6, 4 and 8. Just like that. Moving on to our parabolas, we have y equals x squared. So let's say, excuse me, we had the x and y values over here, and it was -1, 0, +1, 2, 3, and 4. Usually the numbers over here would be 1, 0, 1, 4, 9, and 16. But if we were to multiply the y value by a certain number, or give it a vertical stretch or compression, it would change that. So let's say we're giving a vertical compression by a factor of 0.5. That would make this value, so it would be 0.5x squared. So this value would be 0.5, still 0, 0.5. 2 value usually would be 4, but now it's 2. Usually 9 would be 4.5. Usually 16, but it turns out to be 8. So if we're going to graph that over here, the -1 starts at 0.5. 0 becomes 0. +1 is 0.5. 2 is 2. 3 is 4.5. And 4 is 8. So you can see how if we continued it on the left side, it turned out to be a parabola.